Good afternoon and welcome everybody. For those who are new to this SMCB platform, let me just say a few words. So SMCB means Statistical Mechanics in Chemistry and Biology. We have been running this seminar series for more than a year now. And the primary objective has been to create a platform where all the researchers in this area have a kind of an informal platform to discuss and exchange ideas. But most importantly, our goal has been to introduce and engage young students and researchers to this emerging area of research. We normally have more talks based on research. We have mostly research talks and seminars, but very recently we have been fortunate to have Professor Biman Bagchi give us a lecture series on this very important topic of non-equilibrium statistical mechanics. We have had so far 2 lectures, and this is the 3rd lecture today. For those who have missed the lecture, these few of the lectures earlier, the recordings are already available in our YouTube channel. And this, of course, all the seminar lectures are going to be available as well. I think there are going to be 1 or 2 more lectures in this series. And then we'll go back to our normal schedule of having research seminars. And for those who have not yet subscribed to our Google group, we have a mailing list which has already more than 400 members. So if you would like to receive future announcements and notifications, I would recommend you to subscribe to that Google group. I'll put that link in the chat box towards the end of the lecture. So with that few words, I now request Professor Bagchi to start the lecture.
Thank you, Shumon. Thank you. So this is the 3rd one. In the beginning, the idea was to explain fluctuation dissipation theorem and relationship to time correlation function. But when I started thinking about it, I thought that a very basic background should be given. So we don't know, as Shumon said, there will be 1 or 2, but that's more. I don't know how it will go. It's a huge subject. And I believe that the majority of the audience and whom I have in mind, because the title of my book, Non-Equilibrium StatMech book, will be also the Non-Equilibrium StatMech for, and then lower alphabets, lower size alphabets for chemistry and biology. So it is little bit of that in mind, and that actually defines, subject to subjects, both equilibrium and non-equilibrium statistical mechanics differ considerably. Like mathematics, mathematics for biologists, mathematics for chemists, and so they're different kind of things. And while you may object to this kind of a specialization, but it seems like necessary sometimes, at least in the beginning, then you can make it bigger, and because it's also easier for people to relate to the subjects they are studying. When they see that a theory is being developed and applied to the problems that they are trying to understand, then that makes a lot more sense than an abstract thing. Just we are having this discussion on Boltzmann H theorem. It's kind of abstract, but you have to put it in the proper perspective, then things make a little bit more sense. So I'll very quickly go through, because I have a lot to do today, but very quickly go through a part of the introduction to put people in the perspective, because I myself tend to forget, because it's almost, I think, a month before the last lecture. Or more than a month, I believe. Okay, now, so what we started, that this very short course and TDSM and all these things. So basically, one thing is that it is valid, as you can see from the applications. This is to a great extent is a physical chemistry, chemical physics kind of, a bit biology, biophysics, that kind of thing. These are the huge number of areas where it is used. And why you would like to unify it? Because once you unify it, it's a great advantage. You see the same equations I use in nucleation. The same equation I write in, say, for example, is a very interesting thing. When you do the Lindemann mechanism of immunomolecular reactions and Michaelis-Menten theory of enzyme catalysis, nucleation, everything goes through the same path, some kind of Nast equation or Smolakowski equation, exactly same steady state approximation. So suddenly you see Michael has mentioned nucleation, maybe spiral decomposition, if the Lindemann unimolecular reaction, RRK, many things just together at once capsule. Similarly, when you talk of spectroscopy line shape, if you think it in terms of time correlation function formulation, which is derived and that you find in my molecular relaxation liquids book, which anybody wants, I can give. It is a time correlation function formulation which unifies everything. So once you know the basic thing, then everything becomes very simple. But somebody need to tell you that with certain amount of understanding should be imparted to the student, to be given to the student, so the student can start thinking. But that is not okay. So that is one of the things, and this is the thing. I'll come to this again. So I'm going to put that there is relation between experiment and theory, many different experiments and many different theories, many different kind of thing that I already talked about. This is what exactly I was talking, experiment and theory in context of spectroscopy. That we do the Fermi-Golden rule and the time correlation, and then everything becomes the same. All the Raman spectroscopy, infrared spectroscopy, all becomes the same. Okay. And this I'll come to really aspect, and there are some examples of the things. And the basics we did with essentially Fermi-Golden. We did in the Boltzmann, Maxwell, Boltzmann, Einstein, Willard Gibbs, this kind of who started the groundwork. We talked of time average and ensemble average, which was the Willard Gibbs things. Boltzmann did time averaging, but that could not be proposed. And Gibbs was smart to realize that that path, which led to the great papers of Boltzmann and also to suicide and frustration, that cannot be done. And so he introduced this one of the most brilliant idea of science. It's not really realized how brilliant this is this ensemble average concept. And then enough number of ensemble captures enough number of microscopic states, but then you have to connect it with algebraic hypothesis. And this particular thing is equally important in equilibrium statistical mechanics and in non-equilibrium statistical mechanics. Einstein introduced the concept of fluctuations, and then delta E squared is CV, which is, so these are the response functions and equilibrium response function. That means when you perturb the system, how much is the change, and that is core of our industrial chemical everything, and that is delta E squared CV. Okay, and Einstein introduced that, and then many other things happened, Brownian motion also. So, and these, I was saying that we'll do today the much of non-equilibrium statistical mechanics in terms of time correlation functions, and that's one of the things that time correlation function and linear response theory are both connected, and everything goes through those two things. So the mapping that I'm doing with equilibrium response functions like specific heat and thermal isothermal compressibility, dielectric constant to the dynamic response functions, which are fluctuations, energy, and other things. They are just beautiful. They are going one and the other. They are essentially two sides of the same coin. Okay, and there are fluctuations. And we'll consider that how you perturb something non-equilibrium, and that is the same kind of experiments we do to do the specific heat. You give heat and get the temperature rise. Okay, so they are the same thing. And this is another example of non-equilibrium things. Then I talked about concept of random variables, joint power distribution, conditional probability, and central limit theorem, Gauss-Markov-Group's theorem, regression analysis. I'll do towards the end a little later to be okay. Then books are that, and concept of phase space. So our sample space is our phase space. That's why we are define everything, and the way the phase space is explored by the trajectory. Okay. And So there are these are the things we did: conditional probability, and we said that conditional probability is very important because that's where we get a radial distribution function. That's where we get time correlation functions. The conditional probability of probability theory is translated into statistical mechanics and giving rise to those kind of correlations. Okay, this is very important that you understand that. Conditional probability is taught in 11th or 12th grade. Central limit theorem, Loop's theorem is an amazingly beautiful thing. These two things, then random walk and diffusion that we did, then non-equilibrium. This is the second lecture we started in non-equilibrium StatMac, and I spent a few minutes starting huge number of examples that taking slides from my own lectures. And this is interesting one that on nitrate people talk mostly on rigid cation, so we started doing it molecular ions like nitrate, acetate, sulfate. Okay. And then how it moves? You need to interaction of these with the solvent, and that's where statistical mechanics comes in. That your ion is interacting with surrounding many surrounding molecules, and you are exploring the average properties. And the way to do average goes through Maxwell, Boltzmann, and Einstein, Willett Gibbs. That's the path. Okay, so path remains the same where the equilibrium and non-equilibrium StatMac. That's one central point. And then there are many other things that are famous. Yeah, for Marcus, he used equilibrium, he used interesting non-equilibrium polarization fluctuation, but actually he did equilibrium StatMac, and essentially at the back was linear response theory. 1956, when he did this work, linear response theory was not formulated. It was ideas were there, but the classic paper came in 1957. So what Rudy Marcus did this beautiful work, essentially, this fluctuation theory. Oh, really beautiful. Okay. Then there is all these things put in why it is applicable, put in folding, and this into the then Anfinsen hypothesis, Leventhal paradox, all these things put in hydration there. So this every field there are a lot of controversies, and everywhere whenever there is controversy, you needed statistical mechanics to resolve the controversy and little bit of poetry. And so then all the hydrophobic interactions and all these things. There are a lot of questions that are being here. It's a huge feat, and to an extent, the use of computer simulation sometimes gives easy access. But you have to realize this: you need StatMac to really explain your computer simulation result. And that is something which is not always realized. We did force and flux, a little bit of on Sager's relation, and which is he showed that there is a reciprocal hypothesis. This is a beautiful reciprocal theorem, and that we did some, and then we again come back to this one, and we did this was also again we saw then we did little bit of thermodynamics, little bit of hydrodynamics, and that's why we did the Boltzmann-H theorem, because Boltzmann-H theorem was done in the context of Boltzmann kinetic equation, which is given at the last equation. Here is Boltzmann kinetic equation. The basic idea was that when you do F1, the right side become F2, and F2 is then decomposed into F1, and then you have to use this particular inequality to show that this new equation, which goes by the name of Boltzmann kinetic equation. The first equation is essentially trivial. Just a reformulation in a very non-trivial way, of course. Okay, and then this is the first equation you derived on the top, and then you do the hypothesis, then you get the equation shown at the last. And here you can see f log f kind appearing. It's a very smart thing the way he did this showing. So Boltzmann theorem was needed, and he showed further that Boltzmann theorem at equilibrium, Boltzmann function at equilibrium is nothing but entropy. And then you remark that these two are very, and he appealed to Clausius inequality, that in an isolated system, in a non-equilibrium, then entropy will always increase as you go to equilibrium. That's why he also put the minus sign in front of H to make these two look very similar. And then we said that though there are not many things available, we did a lot of work on Boltzmann-H theorem, and these are the graphs. I hope someday it will be in textbooks, saying how each function goes in 3-dimensional, 2-dimensional, 1-dimensional systems of many different things. They are almost, there's fairly universal in their behavior, though there is a sensitivity to intermolecular potential. And then there is a very nice result, which was is the following, that depending on two very completely quite different initially non-equilibrium thing, and we calculate the H function, and they approach through different paths. But when you normalize that and you find that the two quite different initial non-equilibrium distributions approach equilibrium in a very similar way, and that's the linear response. That it does not depend on the magnitude of the displacement. Okay. And then, of course, I talk a little bit of the analytical work, which I'm not going to talk about it. And then kinetic theory of gases, which Boltzmann started with binary collision, was introduced later by these few very smart people, and a lot of work they did, Cohen, Ernst Stockman, Van Beering, and others, who introduced multiple collision, not just binary collision, beyond binary collision, 3 particle, 4 particle, and a series of them they could sum up, and they produced miraculous result like long time tail in Hart's sphere and Hart's velocity collision function. So Boltzmann to kinetic equation, then one can derive from Boltzmann kinetic equation, one can do Navier-Stokes equation, and that was started by none other than David Hilbert and done by Chapman and Cowling. Chapman and Cowling, I got Nobel Prize, I think, for this work. Okay. So then I did a little bit of hydrodynamics, and that, remember, hydrodynamics is essentially actually this equation you can derive from Boltzmann kinetic equation. That's quite a task, difficult task, but not too difficult, because you have to use the collisional in the way Hilbert solved it. He produced collisional invariants, and collisional invariants are nothing but density at 3 moments: density, momentum, and the energy. And then you derive go back to conservation. Now, that's not too surprising. But what is really indeed nice is that you get expression for the stress tensor, momentum relaxation. So middle equation is sometimes called the Navier-Stokes equation itself. These are conservation laws. And then you have to supplement these exact laws with certain approximate things, which are called the constitutive relations, which follow the symmetry properties and certain obvious things that we learn from Fick's law and the diffusion and the Fourier law, that kind of thing, essentially, got to a position dependent, position and time dependent. Okay, Fourier law and all this also are position and time dependent. So it is very, very interesting that how these things are connected. You know, when you begin to see that, you begin to appreciate the flow of the development of these things. And the stress is just the pressure term, and the term, if 2 layers surrounding you, are upper layer and down layer, are in a different velocity, then there will be dissipation. That dissipation is the viscosity, and viscosity in a gradient of the this is a stress of diagonal term, gradient of the velocity. U is the velocity here. Okay, and then these are the equations. Then you linearize it, and you can solve it. You know, one important thing here is that one introduced the principle of local equilibrium, which was used by Chapman, Cowling, and Hilbert, actually first by Hilbert. So this historically all very, very similar things, one borrowed from the other. And then we get back something to Rayleigh spectra. So I have come now to where essentially my review is over. I think I took more than 5 minutes, but it was probably important even for me to put myself in a proper frame of mind to talk about this beautiful subject, which is so deep and so versatile. It's very, very nice, but the technicality always prevents you from appreciating the overall philosophical appeal of the subject. So now here we already have done, we are not done phenomenology. This is one lecture I do, probably that's the last lecture, the Brownian motion and the Langevin equation, Fokker-Planck equation, Small-Gauss equation. We have done a little bit of hydrodynamics. We'll do time correlation function today and linear response. So in fundamental approaches, what is missing here is that we should have done the linear response theory here, and then computer equations and all these things. So as I told last lecture, that if I use the linearized Navier-Stokes equation, what was the idea? The idea was to get certain values. One of them is the, of course, value of the friction in terms of viscosity. And the other one, that was Stokes. The other one was a density correlation function. Now, I think I told you, but let me repeat a very important point here. Why light scattering and how light scattering measures density correlation function. What is connection? That because when you have a density fluctuation, you have regions of high density and low density. And when you have and you can Fourier decompose it. When you have a region of high density and low density, then high density will have a different refractive index, low density will have a different refractive index. There will have different dielectric constant and different index. So they will scatter light in different directions. So that is the origin of light scattering in the liquids. So light scattering that we see in liquids, they intimately connect with the density fluctuation. So then light scattering is used to measure the density fluctuations. Now, what gives rise to density fluctuations? Remember, we had 5 equations in Navier-Stokes equation. 1 is for density and 3 for momentum, 1 for energy. Now, you can, when you do that, you will find that the 3 equations are connected, and other 1 plus 1, they are the transverse, but longitudinal part, because longitudinal momentum is the same as the flow of matter, and that gives rise to density fluctuation. So that naturally gets connected, and when you solve these 3 equations, you get this linear equation, you get this beautiful structure. And this is the Rayleigh spectra. I recap that we start with density fluctuations, we calculated and then we express the light scattering intensity in terms of dynamic structure factor, because what you can say, the light scattering intensity is the square from Fermi-Golden rule, square of the fluctuation, and then that you can put into a time correlation function by a method called Gordon's method. Gordon was the first to popularize it when he was at Harvard. And but this method I have described in my molecular relaxation and liquid, and I've emphasized how important those things are. That how do you get this scattering cross section is related to dynamic structure. So then the whole thing that happened again and again spectroscopy. What we measure is a time correlation function. And how do I get the time correlation function now? Now the fluctuations I told you in refractive index are long wavelength and long time. They are well described by Navier-Stokes hydrodynamics, that kind of hydrodynamics, and that why we are in a solid ground at long wavelength and long time. That indeed works out, and we get the 3 peak Rayleigh spectra. And as I said, this wealth of information, because these are ones that give sound velocity, give you thermal diffusivity, give you sound attenuation coefficient, through which bulk viscosity, and is one of the few or as the only method to get the bulk viscosity. But these are the Navier-Stokes equation hydrodynamics is valid only at long wavelength and long times. It breaks down, and here I showed one that if I plot the central mode, the Rayleigh peak, which is also called heat mode, because of this connection with thermal diffusivity, you say that it will just go up. It will just go up like this, way up, 3 orders of magnitude larger, but it does not happen in real world. It comes down, and that was discovered in 1950 to 53. Van Vleck, in neutron scattering after Second World War, when these neutron scattering sources become available. Okay, so I'll come back to that. Now, I want to then go to slowly to linear response and time correlation function. So linear response is sometimes made a very big fuss about it and make it very vague, but there's nothing vague about it. The first linear response was our Stokes Law in hydrodynamics, which is the relation between if you have a ball and you are pulling it with a string, and as I described last time, that if you pull it at certain force, below certain force, the ball moves with constant velocity when the force is constant. And that is funny because we know that Newton's law tells us when you give force, you should have acceleration. But that is not the case. It is not accelerated, it's constant velocity. That because energy is dissipated. And the relation between these two are given by the Stokes relation. So it is a beautiful. So force is the external perturbation. Velocity is the response. And the response is connected to perturbation of the force linearly. And this is the very first linear response relation that I know of. And so velocity is 1 over zeta, and zeta is the friction. And as I've already told, friction is the response function. It's the different story that Stokes gave Z equal to 6 pi eta r, but people always say Stokes, but people use that without knowing the first one. First one you should know first before you use the second one. Okay, he first derived this or proposed it, then he went to do that, and there are conditions, of course, the strict boundary conditions, and those things I'm not going to go into because okay. Now this is a computer experiment. Essentially, Subhajit did not only in the area of the air, but also in the context of a work we are doing, but also I put it in the book, that here is a real velocity against the force, velocity against force, and you can see, yes, indeed, in a computer simulation you find that there is a beautiful relation between the two, and that is the linear response theory. So now we have done phase space trajectory Liouville equation, conservation of density in phase space, Liouville theorem, use of Hamilton's equation. That's the way the flow chart. You start with in a phase space, in a microscopic description. In microscopic description goes very, very close to hydrodynamic description. This is very important. That conservation of density in Navier-Stokes equation, and here is conservation of density in phase space, is the Liouville theorem, which is like the conservation laws. And then there, of course, you have you can proceed further to Navier-Stokes equation. Here you proceed, you use the Hamilton's equation, which are again exact, and then you derive an equation of motion, which is called Liouville equation, and that takes to BBGKY hierarchy and many other things. Okay, so Liouville equation, I'm not going to do too much of that, but I have that it goes through Hamilton's equation, which is the little bit more general than Newton's equation of motion, but essentially the same thing of gives equation of motion for position and momentum in terms of the Hamiltonian of the system. So your quantum mechanics, actually all these things came out of this for students, and then you can derive this equation I have shown within the box, and that is the Liouville equation. Okay, these are the things which are now going to get a little tough, and I'll try to make it simple and not going to derive too many things. Okay, so basically from that you want to know what is a phase space kind of thing. What are you talking about? What are the density we are talking about? They are nothing but your trajectories. You look at the trajectories and then you say what is the probability in a given box in this kind of system, and then if this in an ergodic system means every part of the phase space is available, then you get this kind of thing. Then also in 2-dimension or 3-dimension, very similar kind of things happen. So these are the density fields. So the density that we are talking at the density of these lines. Okay, so there's nothing mysterious about it. Density in phase space is now accessible because of computer simulation. At one time they are not accessible, and it is a lot of fun to play with that. And okay, now as I said, that what is the partition function to equilibrium statistical mechanics? Time correlation function is to non-equilibrium stat bank. And just like partition function, TCFs are based on the phase space, but now on dynamics. In partition function, you don't need the dynamics, but time correlation function, you need the dynamics. What are the things? Just like response functions, equilibrium response functions are from partition function. Your dynamical response functions, which are transport properties, are from time correlation function. And also the spectroscopy requires the time-dependent statistical mechanics or non-equilibrium statistical mechanics. So both the transport properties and time correlation functions are there. And I told you, I believe, that the time correlation functions are essentially first came in hydrodynamics through Navier-Stokes equation, through the Rayleigh-Benioff spectra. But hydrodynamics cannot calculate the transport properties. They can calculate relation like friction in terms of viscosity, but cannot calculate viscosity. That comes from kinetic theory of gases. That's where Boltzmann, the route through Boltzmann and Ensemble goes. But however, time correlation function is required in spectroscopy. But since hydrodynamics cannot, these two are actually combined later into molecular hydrodynamics, and then later other more sophisticated ways. So these are useful examples of time correlation function: diffusion, velocity correlation function, viscosity, stress Sigma is stress time. I am not defining it here. Stress time coefficient function. Then polarizability leads to dielectric constant is the total dipole moment, time coefficient function. There are many like that. Like electrical conductivity is current coefficient function. Thermal conductivity is thermal current coefficient functions. So all the quantities that we talk or transport properties or our everyday use are in terms of time coefficient function. Okay. Now, how do you define time coefficient function? You define time coefficient function. There is through a trajectory. You follow a trajectory, and I have in my book chapter, if anybody wants, I can start sending them to you. That in a defined through a, you consider a trajectory, and in the trajectory you divide the long trajectory into certain time interval, and that time interval is your time t, and then they are separated by this time t. Then you translate it, and everywhere calculate the A0 AT, and then you divide by the total time and sum it up, and that is what is explained on the right. Now look at the beautiful thing that this energy of the water, energy of how the energy is fluctuating. It's such a noisy, doesn't look like there is any information there, but look at the time correlation function. This is beautiful. That that t equal to 0 value is this specific. So this decay gives you a measure of how things are moving, and that's very important for chemical reaction, bond breaking, and many other things. But look at the beauty coming from this noisy spectrum to the time correlation function. The tremendous reduction and unification of the information content. And then there is other one. It was many times it's more to combine ensemble average and time average. So you start with many different, several different initial distribution point, and then run the trajectory, and then you get the energy of that, and then you define energy function of your initial point, and then each point you run the time correlation function and average by this Boltzmann distribution. This is the other, sometime more used time correlation function. Okay, this is where I think we will stop. Is just the last slide where we stopped last time. So one very important thing is that time correlation functions at equilibrium has very beautiful properties. One of them, time translation property. At equilibrium, it depends only on the time interval. When here is a proof of that, and the proof goes through a self-adjoint property of Liouville equation. A Liouville operator is self-adjoint, and that is used by turn around things and then show that recombine things. And you can do the is given here. It will be in the recorded lecture, and the proof that it depends only on the time gap. Then there's a beautiful called time reversal symmetry, which is a parity, that A0 BT, that is connected. If you can, I can go right and left array of the time, then it is connected. It makes sense with the time translation symmetry itself. There are other very important properties. One property is that if I have two dynamical variables, A and B, and they have different reflection property, say in XY plane, then that will be 0. So all these, so there are 5 such beautiful properties. One of them is, it starts with the adjoint property. Next is the time translation symmetry, then time reversal symmetry, then this plane symmetry. I forgot the other one. And these are routinely used in this. These two particular, I also the reflections also I have used, but these two are routinely used in the time dependent statistical mechanics in our manipulation. Okay, so there are 2 important time correlation functions that I'm going to spend some time on, and one of them is the same good old Rayleigh-Benoist spectrum. Very interesting, and it was Dijan who found out that doesn't work, as we'll talk a little bit. But more importantly, this is the one which also got much of the work on glass transition, cage effect, and many things in a broadly. People sometimes don't want to tell you that how simple these things are and how they evolve. And when you put in historical perspective, things are your own contribution become minuscule. That's why people don't do it. You kind of see that in the whole grand landscape, you are not even a point. Rabindranath has a great poem called Boshundhara. Amare Firaye Lao. So where he's saying that it is Ajimamo Janmudi. Okay, whatever. So he was saying that all of us is just a small dust kind of thing, a point in eternal thing, and we all disappear. These are he always had that thing in his mind, that the transient nature of life and his contributions. But we always say how big we have done in science. But if you really look everything into perspective, you see really what one still doing is probably not even a delta function, delta contribution we are making, or epsilon. Okay, coming back to Navier-Stokes equation, the density time correlation function with Laplace Fourier transform. Of course, I should add that even if we are adding epsilon and delta, I think it's a kind of a not fair not to work hard and not to do justice. Rabindranath said that exactly that thing, that তোমার আসনের যদি যোগ্য মূল্য দিয়ে থাকে, I have given true price for the place you have given me in this universe. তাহলে দিও আমার কপালে মাটির তিলক, then please give one dot, bindi on my forehead in your own hand. And সেটাও যাবে মিলিয়ে, that will also disappear like everything else. But he did say তোমার আসনের যোগ্য মূল্য যদি দিয়ে থাকে. That's a very important thing. Okay. So what we did in irregular spectra is the dynamic structure factor, FKT, del rho minus K, del rho KT. This same thing, maybe a Stokes equation, is the Fourier transform. And del rho is the fluctuation, and fluctuation is del rho is position rho r at a position r, rho r t equal to rho average plus delta. That is the definition of delta. And here is the Fourier transform. Okay, so here is a density fluctuation of scattering phenomena. I said, you remember that I take a small sphere volume, and their density is increasing and decreasing. And if I take a diameter L or radius, I might whatever, and then so by choosing K, I can choose my L. Hydrodynamics K is K going to 0 and L goes to infinity. So this is a essence. And then how do I think of fluctuation? This is extremely important, very simple thing. The way you think of fluctuation, think of free energy of the fluctuation. So free energy of fluctuation on the fx, the little y, these are all the equations written by my hand. I didn't take my help of students, so you can see the quality is far worse than what my students would write. So fx bar, which is the van der Waals kind of thing, or Landau, that I can calculate the free energy at a given average value of quantity x. Our case, x is density, or you can have anything, orientation. Then your first derivative will be 0, f prime x, because I have an equilibrium. But the second derivative is very important. That is delta x square and second derivative of force. And second derivative of force are the spring constants or the response functions. So the average value of x and van der Waals or Landau is the equation of state and thermodynamics. But it is the force, the fluctuation, that is determining the dynamics. So dynamics of density relaxation determine the force constant of the density fluctuations. The important density correlation is another important thing is the self-dynamic structure factor, FSK. So it's the important, another important. So I use different notation, rho for the collective density and rho for the n for the tag particle density. Okay. Now, why it is so important that I'm spending so much time on this? In addition to their important, there is one very nice little trick that you students should play. The easy approach initiated by Dijan is that has been used by Dijan in pneumatic and liquid crystal hydrodynamics, and then done by Dijan's book. You will find these kind of things. So see what is Dijan did, and it's amazing what he did and how it became so beautiful. I'm going to tell you. So I write an equation. I say my density, that local L, depends on two things. One, the particle diffusing in and out, and it is also how much force is holding that fluctuation, which is the force constant I already told you. Now, in dense liquids, I have a measure of that force, an approximate measure, but a measure, and that is given below. It is in terms of the two-particle direct correlation function. This is a God-given equation, that one I've written at the last equation. The force, F is force, that's why it's a bold, then is a gradient of this, that because effective free energy is minus without the gradient. Okay, so here I've written the force again. V effective is this minus minus, and C capital what is whatever is the direct correlation function. This equation now can be linearized, the one within the box, and it can be solved, and it gives rise to the beautiful equation. D minus, but D here in a small length scale, D is the diffusion. It is not thermal diffusivity and Navier-Stokes equation. And direct correlation function is a very, very short range function. So I get A now, which is valid in the large wave number. Why did Dijan bother about large wave number? Because neutron scattering was looking at a large wave number, you know, of the molecular length scale. And there you find D by SK. So suddenly thermal diffusivity is replaced by cell diffusion with a term SQ, which has a sharp peak at near 2 pi by sigma. Rest is the same. But thermal diffusivity is 3 orders of magnitude larger than cell diffusion. That is 10 to the minus 2 centimeters per square. It is 10 to the minus 5. So suddenly you have a tremendous narrowing of the spectrum, and that's called Dijan narrowing. And so it's a contrasted relevant spectrum is a much faster decay rate. Okay, what is going on? This is extremely important point, and is one of the very important point for present modern research in liquids and biology, that what people do. At large wave numbers, small separations, the heat mode degenerates into cell diffusion. This is a beautiful language written by Cohen Dorfman. That was Cohen and Decipher. A beautiful language. Heat mode degenerates into cell diffusion mode. That means heat mode becomes a cell diffusion mode. Why? This is because at very small length scale, only number conservation is obeyed. Energy and momentum are obeyed at longer length scale. They are no constraint. So this is the basic ansatz where many things started. Molecular hydrodynamics leading to mode coupling theory. Many things has to obey that. So next is the current time correlation function. I just want to go back and show one thing here before I proceed further. I had it here, but I deleted here. So the look at this sudden decrease of the heat mode. ZH is the width of the central peak, the Rayleigh peak. That width goes to 0. So what does it mean? That means density relaxation at large wave numbers is very small. What does it mean? It means that you have something which is holding it back. What is holding it back is the cage that has formed and large density. And it is the cage that slows down density relaxation and the narrowing of heat mode. And that is the one that ultimately leads to glass transition. But you don't have to go to glass transition. Even at high density, most of our properties are dictated by near K2 pi by sigma and this breakdown. Okay. Now what I'll do, I'll further go to share my some of my notes and so now that is very interesting. I got it. So I'll do first I'll do a little bit more of time correlation. I think you can see it. Huh?
Yes, we can see.
Okay. So there are many things done here, like details of in chapter I have done that the self-adjoint property, as I was saying, that we have to prove the self-adjointness of the Liouville operator. That is one of the reasons it is put an IL and all these things. There are a lot of things, smart thing went into it. Then stationary property, I already discussed the proof a little bit. Then I have time reversal symmetry or parity, and several other properties that comes in. And time derivative, another property of time correlation function. And this is a beauty that shows that the time derivative CABT, when you take the time derivative and it becomes minus CAB minus T. So first equation in equation 8.52 is the parity And second one is the time derivative. And this is extremely important. We use that a lot. So and time correlation functions is amplitude is conserved, which is shown here as it lies on a circle, and that because e to the ILT rotates. This is just like e to the I theta, right? Okay, and then physical observables from time correlation function that I already talked about, diffusion, but here is the proof of the diffusion. You start with Einstein's mean square property, and then you write down and do these integrations, and you get the time correlation function. Okay, then you have viscosity, and which is the stress test, shear and bar. So they are stress test time correlation functions. Okay, then dielectric susceptibility. This is alpha is moment correlation function, and you get the thing. Okay, then you have electrical conductivity, as I already said, electrical kind correlation function. Friction, this is approximate, but there's a beautiful way of get the friction, and this is why linear response. Again, use this like diffusion, that acceleration, mass times velocity, the acceleration velocity of particle is minus friction, and then random force RT. Okay, and that is friction is given by force correlation function. The thing that always you have to remember that it is the conjugate quantity that comes, in conductivity, flux is the conjugate quantity, then dielectric polarizability is the conjugate quantity. That means when you put an electric field, then you create a polarization. When you create a stress, the liquid flows with the viscosity, and that is determined by viscosity. So everywhere it is the conjugate property. So it is not very difficult to write down, at least without the prefactor, what is the time correlation function of these. So then there are certain things which are very important. That time correlation function is very difficult to calculate. It is a long time to algorithm. Many people are trying on that. But you can do an exact short time expansion, and which is extremely valuable. Because the short time, just like Boltzmann realized long time ago, is given by few conditions. And that is one can do, and one can show that they have the expansion of the following type. I just want to show if I have the so this is the kind of expansion, and these are the different time derivatives. This is a short time expansion. Beyond a point, it's not beyond t to the power 4, n equal to 2. It's not they are all even functions because of the same parity that we talked about. And then the hydrodynamics. And one important thing is that in one case, you can calculate the time correlation function explicitly. And that is a particle in a harmonic oscillator. This was done by Chandrasekhar in his book. And that is worth doing, that you can explicitly calculate using Hamilton's equation of motion. You can solve everything, and you can calculate explicitly the time correlation function. And that time correlation function is given by here, the equation, the 8.53. Very simple, but you can do it explicitly. So K is the force constant related to omega. So then there is an algorithm, how, as I was saying, to calculate the time correlation function. So the other time correlation function we calculate, many people doing the research all the time, is the rotational time correlation function. And the rotational time correlation function has, I won't have the time to do that, but that also has beautiful properties and is used in, detected in many places. It's depolarization, anisotropy depolarization, as I said already, dielectric relaxation. So next I'll go to a little bit more of time correlation function. And so I want to show you some density time correlation function. So it's a little bit, I went a little bit far before, I should have gone 8, but this is the same thing here. Now, this is the collective density correlation function. What I want to tell you, that low density, this has a beautiful decay, which is nearly exponential, even at large scale. However, when you go to dense liquid near glass transition, see how much it, and this particular graph I'm showing you has been a subject of tremendous discussion over the years, more among physicists than among physical chemists, but a large number of physical chemists also got involved in it. So what happened when you go to in a supercooled liquid, not fully glass transition. Then you find that it has a 3-step structure. Sometimes it is called ladder structure. You have a plateau, which is the manifestation of the gauge. So initially ballistic, the particle, the density kind of rattle around, the potential in the force constant, I already explained by Landau. Then they have certain damped harmonic oscillation because of the fluctuations are now start to get correlated, and that has a dependence, time dependence, and functional form, which is non-exponential, called beta relaxation. But then the plateau is after the first part is over. So beta relaxation, you can say as it's like a compressibility of the liquid. It's a beautiful picture you can have. But then when this is all over, density did not relax fully because it has to flow, but it could not flow. Everything is very slow. So then it stays there for a long time, and that is called plateau. And then you ultimately large-scale density fluctuations happen, and it decay with a long time, and that is called alpha relaxation. That has many components of it, this alpha relaxation. So this, I want to just tell you how sensitive dynamic structure factor is to many details of these have been observed in neutron scattering experiments. I also just want to show you the single particle relaxation time, FSK. And this FSK, this is structure factor, SK, sharply peaked. GR is almost very similar to this. Fourier transform of GR is structure factor. GR is a radial distribution function. Fourier transform structure factor. Structure factor is the one detected experimentally. And it has very sharp peak at the 2 pi by sigma, nearest neighbor, slightly more than 2 pi by sigma. And this is the much of the experiment we do near this peak, where the scattering cross section is large, and you can have unambiguous detection of the incoherent. And this is this appearance of the ladder. And another beautiful universality is that when you go to really supercooled dense liquid, then FSKT and FKT are almost the same. They become almost indistinguishable. Initial part, they are still different. But after say 10 picosecond, initial part is over. Then the self and dynamic structure factor is essentially the same, because what is governed, they govern are essentially by a memory function, which you are not going to go into. Okay, this for some reason went back. Okay, and so this is what, and then also here also you can get the short time expansion, and short time expansion omega square is essentially the force constant. As I was talking, and this is the Einstein, called Einstein frequency. Then you have a omega 4, and this thing is omega square is exactly doable. That is just kBT k square by m. This is always used. What is interesting is the same thing you get in collective dynamic structure factor, and you have the same thing is kBT m square by sk, msk. So a lot of similarity between them and the dynamic structure factor. And this is something, force. Actually, today is very interesting. Today in our morning group meeting, we discussed this thing, and I couldn't remember why this exact expression. So the mean square force on a particle is just this quantity, beautiful. So we are talking of force now. Mean square force is omega naught square and omega, and this is del square u. Del square u, of course, you have to you can get in terms of okay. By what I'm saying, I'm mumbling a little bit in terms of that you have to get in terms of radial distribution function and or calculating computer. Okay, so till now I have done the time correlation functions, and I have now spent about 55 minutes. I'll take 15 more minutes because, as I said, I would like to go into A. So now, and you have to do the simple limits. And one of my purpose of writing the book essentially is, you can probably see it will be a little disorganized, I think, even at the very end. But I would be able to put all the special cases because I want students to know, because I got benefited tremendously by working out these special cases. Like I said, particle in harmonic oscillation, free particle case, where you can get the solution. You can work out the equation. You can work out the phase space things, and you can get an exact expression. And lo and behold, you find that yes, it makes a lot of sense. Then you can, once you train yourself a little bit by doing these exactly solvable models, like I told you, Ising model is a wonderful model we use all the time. This exactly solvable model is the one that that really you must go through. And then, of course, otherwise you won't understand what you're getting out of the solutions. Okay, so now I've told you about time collision function, but all the time I'm also telling you about the all the time also telling you linear response theory, fluctuation distribution theorem. Now, it's a chicken and egg problem. Who comes first? Now, if you look historically, then linear response theory came first because that came with Onsager. But around the same time, time correlation function was done. It was not called time correlation function in the Rayleigh spectrum. Really, Lord really worked this out, I think, in late teens or early 20s. Onsager did the linear response regression hypothesis, which I'll tell you about linear, the same as linear response in 5 minutes. So I again and again really implore people to take the whole thing in a totality. So again, chicken and egg problem, coming back to that, time correlation function and linear response theory, they went hand in hand. And linear response theory and time. But however, the connection between them two were not made. Connection between two of them were made in the classic paper 1957 by Enrico Cupo. And that's what we are going to do now. If I can get that. Okay. Not bad. I think I'm pretty pleased with myself. Okay. So let me read this linear response theory and fluctuation distribution theorem, and then connect time collision function. If I can do that, that my job today is done. Okay. So linear response theory provides us a quantitative method to calculate the response function to an external perturbation in terms of properties of the system and equilibrium. That is the linear response theory. It's both equilibrium and non-equilibrium. Okay. The fluctuation distribution theory establishes quantitative relation for transport properties in terms of, you should always look at these two beautiful things: transport property and time collision function and linear response. They are all kind of all together. Quantitative relation of transport in terms of the time collision function. They are of great practical help. In fact, the linear response theory can be considered as the direct generation of the statistical mechanical expression of equilibrium response functions that I have said, like specific heat, compressibility, susceptibility. Both LRT and FT are remarkable, are invariably connected with the name of Einstein, Onsager, and Cupo, who contributed to the development of these theories from fundamental principles. And as somebody was asking about H function is, in a way, is a time correlation function, but it is a, okay, whatever. That I want to go into it. Okay, regression hypothesis Onsager. So these are the names. Liouville equation for density matrix. Development parallels the perturbation theories in quantum mechanics. Linear response theory is also a first order perturbation theory. Very important to understand that. And that's why all the Fermi-Goldman rule and all these things we use and get away. And even though they are first order perturbation theory, in statistical mechanics, because of the presence of the force constants that I talked about, first order perturbation theory is remarkably successful. That because of the large force constant, that because of lambda, free energy expansion. Okay. Same formalism can be used to derive relation between fluctuation and dissipation, which is called the fluctuation dissipation theory. Okay. All right. Let's get into business now. So derivation of linear response theory. So we start with the perturbation. So we have an external field FT, say an electric field, and I have some dipoles, and you're acting on the dipoles, and you oscillate an electric field. So I have then the Hamiltonian of the system. H0 is in the absence of the electric field, then it becomes H0 plus HT. And H prime T is the time-dependent part of the Hamiltonian. And this is, I can say that F is an external force, is like electric field, and A would be then polarization. So important thing to know here that A is dependent on the details phase space of the system. Okay, AFR is a position dependence. AFR comes from external source, but A is a mechanical value. Okay, so there is a Fourier decompose and all these things, and then further Fourier both K and omega. Okay, but here is the fun starts. I write the Liouville equation df dt equal to IL FNT. In particular, N is there put gloriously to confuse people, but it means all we are talking of the phase space, all the N particle. So it is not Boltzmann. Boltzmann started F1, N equal to 1 in Boltzmann kind of equation. And he landed up in F2, and then he did the molecular chaos. We are doing the full phase space. Okay. So now, you look at that, if L has, both F and L has the information of the phase space in the absence of the force, and of course the perturbation due to the force. Okay, I just written that thing down explicitly. Now another fun part. I come just like in perturbation theory, exactly psi equal to psi naught plus psi prime, right? Psi 1. So my distribution function is f naught plus delta f. Delta f is the perturbation. Okay. Now I write the equation df dt, then is df of dt plus these things. Then I put back this thing into here. These condition. I get 4 terms. Okay, the 2 into 2. And so this gets, these are the unperturbed Liouville equation. They cancel each other. This is a linear because L naught has no perturbation. Del F is the perturbation. Okay. And then here you have the perturbation. I've written, you could have written just Liouville operator L1 F naught. It is actually L1 F naught, but it in terms of Poisson bracket. So this first order in perturbation, because A is the perturbation, A and F. Okay. This is the nonlinear term. You see, I have both F and delta F. So this is the second order term. So one term goes to 0, get cancelled by F naught goes to 0, get cancelled. These I ignored because it's a second order term. So I have now dt del F, I have 2, both are first order. Exactly your quantum mechanics. Exact. Now, what I'll be doing, your time dependent, actually time dependent quantum mechanics. So I now have this equation after linearization. I have this equation, equation 11.7. Now I solve it formally. I solve it formally in those who remember Dirac's solution of time dependent Schrodinger equation. It's the same thing. And I solve it formally. You can easily check it by direct putting back into the equation. So this is the solution, formal solution of the time perturbation, del F. Now I go and a little bit look into AF naught, and this is a Poisson bracket. And I know how to do Poisson bracket. I know it is here DRI, here DPI, here DPI, DRI. I would have preferred Q, but okay, whatever it is. Say 11.9, and then I rewrite it. It is IL naught, because this is a trick. F naught equilibrium is e to the power minus beta h. So I take the derivative, I get dH dP. Okay. Then I have e to the power minus beta h left. So that become F naught. So everywhere I play that trick. And when I play that trick, this is again the Liouville operator. Exactly. So I L naught AF. So I get an equation. This term is now expressed very neatly in terms of, because I have IL not yet come here, it doesn't become A dot. Well and good. Then now what do? I want to see what is the perturbation of a property B. So the game is the following. I am putting an external field. Listen very carefully. I'm putting an external field that is coupled to A, which is the mechanical variable like polarization. Now I want to calculate a different property. That property is B. That property has an equilibrium value, but that is going to be perturbed because my external electric field, and I'm going to calculate that. So the first stage, I put a field that couples to the system through a function A. but function B, because all are the same. They are all properties of R and P. So then I write that, of course, I know how to do del Pt because I know del Fn. So I do the integration over phase space. And then I say, aha, I know del Fn because that's I derived it just before. And that is this quantity. And now I have made the dot very proud. And then I use the hermeticity self-adjoint property, bring it here. And lo and behold, now I have these things. I have taken out. This is the external field from minus m to t. This is my phase space integral. I have this averaging over there. So this is nothing but it. These become bt minus s. I get a time correlation function. So this phi is just after effect function we Kubo defined. And then I get a time correlation function. So delta bt, my observed response, is nothing but a time correlation function. So this is what I have been trying to beat into your head, that the observed property is a time correlation function. And here's the proof. And this, I think, believe as good, as beautiful a proof as anything in the world. And with that, I have done my much of the job today. So, but I'll continue a few more minutes. So bear with me. So the right hand side is the time correlation function. Okay. Now the thermal, these are thermal averages, the ensemble averages involved here. And beauty is that this thing, my L0 is at equilibrium. So this time correlation function here is a phase space average. That means I get my response due to an external perturbation in terms of equilibrium quantities. I repeat, perturbation in terms of equilibrium properties, just like specific heat. Specific is an equilibrium property. So I put an heat, temperature goes up. How much goes up? Gives you an equilibrium property. You put a magnetic field or electric field, polarization. How much polarization? That's given by the susceptibility. That's an equilibrium property. This you should certainly appreciate and the beauty, because this should be the bread and butter. If you think like that, you will be able to go far. Otherwise, you will be a slave. So this is Kubo's definition. Now we'll go a little bit more of that, but we have established the main thing I wanted to do today is that establish the relation between time correlation function and linear response theory. Why linear response? Because I kept on the F now, delta F. That is linear. So I have a linear, but their response is at a level of phase space. If you are, it is actually in phase space, but we make certain approximations. Okay. So this is done. This is linear response theory. Then we can make it time dependent mode, force time dependent position, and I can make it a. This is now beginning to look like Cramer's conic relations or all the things that you see in solid-state physics books. It's the same thing. Exactly the same thing. That these response functions. And so when A is the same, then this is these things. So basically, then what the, let me summarize the step we followed. We started Liouville equation and the Liouville operator. And these beautiful things were mostly made by Shomok. Perturbation is H0 plus H prime. F is F0 plus del F. LE is the full density matrix, Liouville equation. Linearize LE and find formal solution that we did. Find the response that leads to time correlation function. Is a neat and beautiful flow diagram. I'm very proud of that. Now we go to fluctuation distribution theorem. Fluctuation distribution theorem, they are often called Kubo's fluctuation displacement theorem. Kubo produced two of them. But the first one is not Kubo's fluctuation distribution theorem. First thing is Langevin equation, and that's probably should go to Einstein-Langevin, their thing. So this is the relation, but Kubo, according to Kubo, there is a relation between mobility and velocity time correlation function. And this is the same thing, the Stokes Law that I gave you. And I said that's the first linear response. And so this is the relation between mobility and velocity, TCF, is the first fluctuation distribution theorem. And second fluctuation distribution theorem, he goes for the we probably do a little bit. Second, fluctuation distribution. So fluctuation distribution theorem is a statement of relation between continuous fluctuations in a system and various distribution functions. So it's a class of theorems. Friction is one of them. Dielectric relaxation is one of them. Viscosity is one of them. So all these things are these kind of things. And so there we can make it a little bit more quantitative in terms of the time correlation function, but this is the same thing. I just want to end with one little thing. This I said I'll come back to the Onsager's regression hypothesis. This is something is misunderstood. So I want to put it in the Onsager's paper and Kubo's work. And this is very, very neat, beautiful thing. So regression hypothesis is what? This amazing of, Rudy Marcus theory is exactly the same thing. And Rudy Marcus was always worried for a very long time that how come his non-equilibrium fluctuation theory is working so well. Because I told you he did it in 1955. Papers came out in 56. That is before Kubo's theory. So basic idea of the regression hypothesis is that I have a quantity M. You can call it moment. Then I can have a perturbation, as I showed in Boltzmann function. I already showed that you have a finite perturbation. And then you define a non-equilibrium function. That is right-hand side of the equation 11.21, delta, capital delta empty by delta 0. But I can also think of very spontaneous small fluctuations. And that is delta m0. Then I can define a time correlation function. That's what I say, that Onsager's thing essentially has such a neat meaning in terms of time correlation function. So delta and these two are equal. And this is actually Onsager's regression hypothesis. And this is also linear response theory. So equation 11.21 summarizes huge number of what we do, what we believe, our bread and butter. And this is the application is widely used. Many cases, these things are used. Now, what is the reason for wide validity of linear response theory in fluctuations? So this is what I already told, that this is because there is a force constant. There is, which is Landau's, the second moment of the second expansion of the fluctuation. That is the main thing. That is that you get such a wide applicability. However, that force constant disappears near a phase transition. And near a phase transition, linear response theory breaks down. And you have to do a lot more work, especially dynamical critical phenomena that was done by Kadanoff and Swift, that you have to reconstruct but still relays heat mode degenerates into cell diffusion mode. Now you again talk of degeneration, or rather conversion of one into different other modes. And that's how renormalization theory, dynamical critical phenomena is done. There's again a beautiful thing. One day probably I'll just give it lecture on that, but that is not in this series. So this is the end of today's lecture, and I'm very pleased with myself that I could do time correlation function, though I know I can do the full proof, but it would have been very boring. But I have done, I think, about 30–40% of the proof, and that's enough for any serious student to find things out. So this is, I'll stop share here and give it back to Suman.
Yeah, thank you, Professor Bagchi. Excellent lecture. So now we have a few questions in the chat box. Let me then read them. So Kriti Alam has a question that how is the time-dependent density functional theory, or maybe classical density functional theory, is different from quantum mechanical density functional theory?
Yeah, in both have the singlet density, but in the classical density functional theory, we have an advantage. The advantage is that we have the equilibrium correlation functions, like pair correlation function. We have a direct correlation function. We have no analogy with respect to that. Here, we minimize the free energy because we have temperature. in quantum density functional theory, we minimize the energy because they don't have entropy, because they are, most of them electronic gap is so much, the temperature is not important. So basic idea is that there is a minimization principle. In my case, it is the free energy. In quantum case, it is the energy. And advantage in our case is that we have the particle correlation function. So our thing is much more robust and we can do a lot more analytically. There, I think, to a great extent, things are done numerically, because to take into correlation quantum mechanically, analytically, I think is probably not fully developed yet.
Yeah. So then, and the next question is from Ilka. Is there any condition when we apply force but energy dissipate and acceleration does not occur?
No, acceleration is not happening. That's the whole linear Stokes law. So acceleration is not there anyway. I applying force, Newton says it should accelerate, but we find in real world, when you pull a plastic or iron ball, do the experiment today, you'll see you put the force, but it moves at the constant velocity. That's the Stokes law, and that because the energy you are giving to the system is getting dissipated. It's actually very nice. I know we are discussing these things ourselves in the group tomorrow morning, that you take in a 5,000 particles, you say 10 particles and you pull it, then you find when the force becomes certain thing, then there's a flow is generated. And as soon as the flow generates, your linear response theory breaks down, because you are perturbing the system. No longer I can talk of the fusion. Actually, that is in a certain way active matter people do. There is an effective term. Yeah, I think dissipation is root cause that you don't have acceleration.
Yeah. If there are any other question, you can raise your hand and ask the question yourself. Any other question? Okay, maybe I'll ask something which might be a bit of philosophical question maybe. So this is quite interesting that different transport properties or response functions are related to different kinds of correlation functions. So now when you have a new experimental measurement, let's say new technique, and new techniques are coming. So how do you think about it, that how to develop? So when you know a property, can we reverse engineer and how to find out that which time correlation function I should calculate? How to derive that?
Great question. And so yeah. So let us think of the first most fundamental time correlation function that we actually do, which is the how does the scattering things. That's one of the first one. Now, how did these things come about? This is described in Barnard Pecora, chapter 2 or so. Then you think that, okay, I have a scattering cross section. What is scattering? Then you knew already that, okay, you know already that this is what Rayleigh and all these people worked out, of course. That scattering is by density fluctuation. So then you go and do try to relate the scattering through the density. So there are two steps then. One is to find out what is the root cause or the effect that you are seeing in experiment. And then there is that so you derive a relation now between the dynamic correlation function. Let me do a little bit now so that I can. So you can see the root cause, because seeing sometimes yourself is really kind of a better than okay. So first stage is when you are doing a new experiment, you have to say, okay, this is my experiment. This is my Hamiltonian, or this is my perturbation. And then what is giving the response? So you have to derive a relation between just like light scattering people or Newton scattering people derive the relation between that and dynamic structure. Okay. Now let me say a better thing in terms of say IR spectroscopy. IR spectroscopy, I put an electric field, and electric field now hits the bond and it absorbs energy. A transition takes place. So now I say, okay, then what are the perturbation? This, how much energy is getting absorbed? I know Fermi-Golden rule. So I write down the Fermi-Goldin coupling VIF square. And then I say, okay, then VIF square have two things. One is the electric field of the light. Another one is the transition probability. Okay. And then I know transition probability is the VIF. That part then I can write in terms of then I can transfer that into energy dipole time collision function. How do I do that? I have mu square coming, and I have e to the power ILT. Then I actually manipulate these things. So same the kind of thing I have done to put it by using this adjoint property and all this into mu 0 mu t. So then I get that there's a prefactor which contains properties of light, E4 or something. Then I get I omega. IR omega is nothing but the prefactor integrated over dt to the power I omega t into dipole time collision function. Exactly same way I do Raman scatter. So you now take your experience that how. So basic idea first is the perturbation, and then from perturbation you derive what your observable relation is between that, and that in our case is the dynamic structure factor or dipole time collision function or polarizability time collision function in terms of Raman. Then you go. So there's as I always say that the road between from theory to experiment or experiment to theory have the two stages. One stage is the first stage where you get the relation, and second stage where you evaluate. First stage is getting the time collision function using Fermi-Goldin rule or things like that. A transition probability will be there, has to be there, and then next is the time collision function. Yeah. It's actually fairly well established and a thing. So this relationship, this I call from the Fermi-Goldin rule to time collision function was done by Roy Gordon in 1960s paper in Journal of Magnetic Resonance. We all learned from that. In my molecular relaxation liquid, the whole picture is given, the flowchart is given, what I told you now. And I have done several examples where I have showed how exactly time collision function works.
Thank you. Okay, so if there are any other question, okay, I guess there are no other questions. So particularly for the students, I'll encourage you to revisit the lecture notes. I mean, I understand these are advanced topics, and if you don't understand, maybe you need to watch the lecture videos a few times. And yeah, and next time, whenever the next lecture happens, we'll announce it in our mailing list and also in the social media. So please watch out for that, and we'll announce it very soon. So with that we thank Professor Bagchi once again, and thank you everybody for joining.
Thanks.
Okay, thank you.
Bye.
Bye. Bye everybody.